Many of you have seen one of these used, and I'm sure many of you even own one of these penetrometers. This is a soil penetrometer that was built back in the mid-80s or early 80s. It only came with one size point fits all, unlike the new models. And this one's actually all aluminum and stainless steel. No plastic parts. And I've got it out here right now because I want to demonstrate that at the bottom of the tine insertion hole there is no resistance created by the downward movement of the tine. The control of the speed of the shaft and the skidding action or scuffing of the tip of the tine creates that ripper scenario where soils are actually lifting behind the movement of the steel. So like with this penetrometer, when you are checking out compaction at the base of this tine on a smart till operation, you will find there is no resistance there. The needle never moves out of the green zone through the bottom of the hole. Other competing tools with different designs of tine cannot achieve the same purpose because they have lost the control of the shaft speed, which regulates the amount of time the tine is inserted and the resulting effect at the bottom of the hole. Okay, so now we're going to shift gears a little bit and we're going to compare and contrast two tines which, when not side by side, would appear very much the same. But I put them together here so that you can see at a glance the differences that have taken place over time in the evolution of this technology. The tine on the right is this on my right is the smart till tine. This bar in the center is just an indicator of the perpendicular to the shaft, which would be holding a series of these assemblies with these tines. And then this is a competing tine that was introduced into the American marketplace in 1988. And you can see right away that they both lean in different directions from the perpendicular. This one 5 degrees to my right, and this one 5 degrees to my left. You can also quickly observe that this beveled edge, which I've painted here so that you can see it more easily, is in the opposite direction. Likewise, if you look at the reverse side of these two tines, you'll see the bevels on the opposite sides have also been reversed. So, other than that, the twist, in other words, the offset in the base of the tine, is identical on these two designs. Out of the 4 design features that we've just touched on, 3 of them have been altered. And that's how this tine was able to achieve its own patent status in 1988. It was granted. And its effects are very different. You recall, we talked about when the tine entered, how this smart till tine displaces soil on the compression thrust side of the tine to accentuate the thrust forces to perform tillage. This contrasting tine parts soil in the opposite direction. So this, when it enters, will put soil on the opposite side of the hole, which, by the way, never moves. There is no force applied to the back side of this tine to fracture that soil. The movement, because of the offset of the shaft, is identical to this tine. They're both moving to my right. So this leaves a ½ inch of soil displaced in a vertical wall, much like you would take mortar or plaster and apply it to a brick. Now, as the tine continues its entry, of course, it begins to intercept soil on this vertical face, as well as on this engaging face, because they're both twisted into the soil. This vertical face is gathering soil against itself, actually increasing the turning ability of the tine. This one is shearing off on the backside and contributing nothing to the turning force or torque of the shaft to introduce other tines that are all fastened together. As a result, this speed of the shaft that uses these tines is increased nearly 50% compared to these. So when you examine the insertion of this tine, you'll see the top elongation of the hole is usually about 8 inches, whereas this one will be 12 or more. in most soils. Now again, looking at the back side, where we talked about the entry edge creating the smeared wall or compacted wall, this one has nothing of that going on. This one comes out of the ground and the soil slips off on this edge, the opposite side, the thrust side of the hole. This one is twisted and the bevel reversed, so it actually comes out against that side of the hole and actually lifts soil or scrapes it and lifts it all the way to the surface of the field. And this is a very characteristic finish, which then has to be dealt with. Planters have to learn to live with those clods. That's what finishing harrows and packers and various things have to deal with behind this operation of this tine. So unfortunately, this is kind of like sharpening a knife backwards, and it doesn't stay sharp like this, and it certainly doesn't self-sharpen like this. The reality is that in a few hundred acres, this edge of this tine becomes rounded because it has worn itself off as it scraped its way up the side of the hole, throwing soil to the top. So you wind up with a rounded edge, which now may or may not throw much soil, but instead separates the soil as it does scrape, and it actually packs the opposite side of the wall. This tine is advertised as having the ability to hold water, and indeed it does. When this tine operates in average soil or slightly above average soil moistures, you can literally put manure or water in the hole and it will sit right there. There is a nice packed surface all the way around the bottle. This one, you can't get anything to stay in the hole because it's full of holes. It is literally a broken glass. So this tine, sold in the marketplace as an aerator, can create fracture forces under very dry conditions, but because of the virtue of its geometry, actually forms a hole and is advertised as having the ability to form a pocket into which you could place things like animal waste. This one cannot do it. This technology fractures soil so effectively that water or manures or any other liquid products rarely can get down the hole. They have diffused at the surface so uniformly there's nothing left to go down the hole. Okay, so there you have the compare and contrast between the geometry of the Smart Till and one of the competing products in the marketplace, so that you might know a little more about what you're looking at when you see these things work in the field and what to look for in terms of the soil conditions that it leaves in its wake. Okay, here is a group. I don't know if you can see this, but here is a group of roots. Mm-hmm. See them? Mm-hmm. See how they're clustered here?
They found the hole.
This is right where the tine worked. Mm-hmm. You see where this went? Mm-hmm. This is the longest root on the whole root. But this is where the machine actually broke through any density layers and created a pathway of homogeneous density, the same or similar density, so that the plant would grow fast, uninterrupted, deep. Here I think is another group right here. When you hit that zone, it gets pretty hard to find roots.
Yeah. That's got two of them, doesn't it? It's about
Yes,
right
about
the
over
spacing where it would have.
You had two passes out here too. So. Yeah, I've been watching that since 1984, first time I saw it. And I watched those roots go down through that hole and just keep on going, and I was amazed, absolutely amazed. This is largely a function, as we've been talking about, of working vertically and moving sideways instead of working horizontally. I would be very negligent if I didn't say you can do all of this vertical tillage correctly and then make one pass with some other machine that works this way, and this will not happen.